Hey everyone, welcome. Today we're going to make physics personal. We're going to take those kinematic formulas, the ones that can look kind of scary in a textbook, and turn them into actual tools you can use to understand how things move, from super fast drag racers to the car you're in every day. So, here's our game plan. We'll start with the basics, build up our toolkit of equations, and then we'll put them to work on some really cool real-world examples. And we'll wrap it all up with a little exam prep session to make sure you're ready for anything. Ready? Let's jump right in. Okay, first things first. Before we can do any math, we've got to speak the same language. In physics, setting up clear rules and definitions is absolutely everything. It's how we make sure our numbers actually mean something in the real world. So, to make our lives a whole lot easier, we use a simplified notation. We just decide to start the stopwatch at 0. Makes sense, right? Then, anytime you see that little subscript 0, like on the X or the V, that just means initial or starting. Anything without it is the final value. It's a simple little trick that really cleans up the math. Okay, now this is the big one, the one rule to rule them all for today. Every single equation we're about to talk about only works if acceleration is constant. It's not changing. Now, I know, in the real world, things can get more complicated, but for a ton of situations, like a car hitting the brakes or something falling, assuming constant acceleration is a fantastic approximation. All right, it's time for the main event. Let's build that toolkit. These are the key equations you're going to need to solve pretty much any motion problem that comes your way, as long as acceleration is constant. Kicking things off, we have a real classic. This one is perfect. It gives you a direct link between your final velocity, your starting velocity, your acceleration, and time. Wondering how fast a car is going after accelerating for 5 seconds? This equation has your back. Next up is this powerhouse. This equation is all about finding where something ends up, its final position or its displacement. And pay close attention to that little t-squared in there. That's huge. It's the reason that when something is accelerating, the distance it covers grows way, way faster over time. And this one's my personal favorite because it's like a secret weapon. We call it the timeless equation. If you've got a problem where you don't know the time, and you don't even need to find it, this formula is your shortcut straight to the answer. It's incredibly useful. And last but not least, we've got this handy little helper that uses average velocity. Now, when, and only when, acceleration is constant, the average velocity is just this simple average of where you started and where you ended. Easy, right? It's another great way to connect position and velocity. Okay, theory is great and all, but let's see what these equations can do in the wild. And let's go somewhere extreme. I'm talking about the insane, super fast world of drag racing. We're going to follow a really simple 3-step strategy. First, just list everything the problem gives you. The dragster starts from rest, so its initial velocity is 0. We've got its acceleration and the time. Second, you play detective and pick the right tool for the job. We want to find the distance, and we know the time, so equation 2 looks perfect. And finally, you just plug in the numbers and solve. And what do we get? 402 meters. Now get this. 402 meters is almost exactly a quarter mile, which is the standard length for a drag strip. We literally just used a bit of math to predict the length of the track. I mean, how cool is that? All right, so we've covered slamming on the gas. What about slamming on the brakes? Now we're going to flip the script and look at the physics of stopping. This is all about deceleration, which is just a fancy word for negative acceleration. Same game plan as before. We list our knowns. Initial velocity is 30 meters per second. We're stopping, so final velocity is 0. And here's the key. Acceleration is negative because it's working against the car's motion. We want the stopping distance, but we don't know the time. So that timeless equation is the perfect choice. So we run the numbers and find the car stops in about 64 meters on dry concrete. But look what happens when the road is wet. The deceleration isn't as strong, and the stopping distance jumps all the way up to 90 meters. That's a massive difference, and it's exactly why you need to give yourself more room in the rain. But hold on a second, we're not done yet. That 64 meters we just calculated, that's the braking distance. That number only starts counting from the moment your foot actually hits the brake pedal. What about the time it takes your brain to see a problem and tell your foot to move? Believe it or not, for an average driver, that reaction time is about half a second. Now, half a second might not sound like much, right? Well, when you're moving at highway speeds, a lot can happen in half a second. You have to remember, for that entire half second, you haven't even touched the brakes. The car is still flying along at a constant 30 meters per second. A simple calculation shows it travels another 15 meters. 15 meters! That's about the length of a city bus, all before you even start to slow down. So let's add it all up. You take that 15 meters from your reaction time and you add it to the 64 meters of actual braking distance. Your new total stopping distance is almost 80 meters. Think about that. That tiny little half second of human reaction time added more than 20% to the total distance you need to stop safely. That's huge. Okay, let's bring it all home and pack up our toolkit so you're ready for your next test or homework assignment. This is everything you need for success. So here they are, your three main equations, your workhorses. And don't forget the three-step process. List your knowns, pick your equation, and then solve. If you stick to this method, you will nail these problems every single time. And before we go, let me give you a heads up on the common mistakes I see students make all the time. Please, don't forget that slowing down means acceleration is negative. Always double-check which velocity is v0 and which is v. Make sure your units all match. And always be on the lookout for those two-part problems that have that sneaky reaction time built in. So I want to leave you with this one last mind-bending idea. Remember that v squared in our key stopping equation? It isn't just for show. It means that doubling your speed doesn't just double your stopping distance. It quadruples it. Think about that relationship, that power of the square. Where else in your life do you see a small change leading to a surprisingly huge result? Once you start looking, you'll see this physics everywhere.